Hello! Last time, we characterized superadditive games that have non-empty cores. We will now extend this to all cooperative games. Recall that in superadditive games with non-empty cores, there is always an outcome in the core with the grand coalition. However, this is not necessarily the case for cooperative games in general. Let's take a look at this example. Let n be 1, 2, 3, and 4, and the value of a coalition is 2 when the size of the coalition is at least 2, and it is 0 otherwise. Now, a previous proposition tells us that coalition structure in the core must have the highest possible value. If we look at the grand coalition, its value is 2. But there is a higher value coalition structure. The value of 1, 2, and then 3, 4 is actually equal to 4. So the grand coalition cannot be in any outcome of the core. Also, the core is non-empty for this game. You can check that with pi equals to 1, 2, and then 3, 4, and x equals to 1, 1, 1, 1, we have an outcome in the core. So checking if the core is non-empty cannot be reduced to checking only the grand coalition. But a nice result is that we can relate this to superadditive games. We first need to define what is a superadditive cover. For any cooperative game NV, its superadditive cover is NV star where, for each subset S of n, V star of S is the maximum of the values of pi over all pi that is a partition of S. For example, the superadditive cover for our example above is NV star where V star of S is equal to 4 when the size of S is 4, it's 2 when the size of S is 2 or 3, and it's 0 when the size of S is 0 or 1. Just to give you an idea of how this is calculated, if we want to find out V star of 1, 2, 3, we look at all possible partitions of 1, 2, 3, there are 5 of them, and look at each of their values. And we pick the maximum one, which is 2. As an exercise, prove that the superadditive cover is indeed superadditive. And here is the main result that links the core of any game with the core of its superadditive cover. A cooperative game NV has a non-empty core if and only if its superadditive cover NV star has a non-empty core. As an example, check that n followed by 1, 1, 1, 1 is in the core of NV star above. For our proof, we will prove one direction and leave some details of the other direction as an exercise. In the forward direction, we assume that NV has a non-empty core. So let pi x be an outcome in the core of NV. And the goal here is to show that when I replace pi by the grand coalition n, it is in the core of NV star. Since NV star is superadditive, x must be in the polyhedron script C we have defined last time. This means we need to show two things. V star of n is equal to x of n, which also shows that it is a valid outcome. And V star of c is less than or equal to x of c for all subsets C of n. We first note that by a previous proposition, V of pi has the maximum value among all partitions of n. So by the definition of the superadditive cover, V star of n is equal to V of pi. We can now prove the two things. First, V star of n is equal to V of pi, which is the sum of all the values of the coalitions in pi. And this is equal to the sum of x of c over all coalitions C in pi. And this is because pi x is in the core, so it is efficient over all the coalitions in pi. And this is equal to the sum of xi's for all I in n. And that is because pi is a partition of n. And this is equal to x of n. So that completes the first thing that we need to show. For our second thing, we let C be any subset of n. We suppose that V star of C is equal to V of pi prime for some partition pi prime of C. Then V star of C is equal to V of pi prime, which is equal to the sum of V of C prime over all C prime in pi prime by definition. And this is less than or equal to the sum of x of C prime over all C prime in pi prime. And that is because pi x is in the core. And this is equal to x of C, because pi prime is a partition of C. So we have proved that nx is in the core of nv star. So the core of nv star is non-empty. And that completes this half of the proof. For the other direction, we suppose that nv star has a non-empty core. Since nv star is superadditive, there exists a payoff vector x such that nx is in the core. By the definition of the superadditive cover, v star of n is equal to v of pi for some partition pi of n. And our goal here is to show that pi x is in the core of nv. There are two things that we need to prove. We need to show that it is a valid outcome. That is, v of c is greater than or equal to x of c for all c in pi. We also need to prove that the core condition is satisfied. That is, v of c is less than or equal to x of c for all c a subset of n. We leave the proof of these as exercises. And that is our proof. So now we can characterize the set of cooperative games that have non-empty cores. A cooperative game has a non-empty core if and only if its superadditive cover is balanced. And the proof is simple. We combine the Bondariva-Shapley theorem with our proposition above. Once again, this is difficult to verify in general. In the next lecture, we'll show a nice result about convex games. And spoiler alert, all convex games have non-empty cores. And we will find a way to construct some of the elements in the core.